Now that we have established a few theoretical results related to what our analysis for compositional data should look like, what kind of spaces we'd like to work in, and what properties those spaces have, such as permutation invariance, scale invariance, and compositional subcoherence, subcompositional coherence, we can now look at the actual methods that would go into doing this. And these will be called the log ratio methods and log ratio analysis. So there's a number of interesting publications and then that are available to study this. First of all, there's of course the book by Aitchison, which is available online, A Concise Guide to Compositional Data Analysis. There's also the very interesting paper by the Barcelona group looking at log ratio transformations in a general sense. We'll see that there are a number of forms of these log ratio transformations, and this paper discusses the various forms available and their properties. In log ratio analysis and in the exploratory data analysis we'll be discussing, and we'll also be looking at biplots. And so I think the original paper by Aitchison and Greenacker is a quite nice introductory and tutorial or educational kind of paper on biplots for compositional data. So in a recap from the previous section, as I mentioned before, is that compositional data requires a definition of a different geometry than we used to, different from the Euclidean geometry. And so that's why calculations need to take place in a different space. These spaces, as I mentioned, have to have certain properties that make sense, such as some compositional coherence, means working with parts should be the same as working with the total, at least should not alter the results, scale invariance, and permutation invariance. So you wonder why log ratios and not ratios. First of all, ratios are not symmetric, while log ratios are symmetric up to a certain sign. So the log of this ratio is the same as the log of that ratio, except for the sign. So that's interesting because then we don't have to worry about what we put in the denominator necessarily. The variance relationships, the variance of log ratios, again, have this symmetric relationship, but the variance, there's no clear relationship between variance of ratios. There's also, for example, we'll talk about the bijective property, which is once I've created log ratios, then I can always go back to the original composition using a simple back transformation. So this back transformation is important in the sense that we'll do in all the computations in this log ratio space and then transform it back into this original space. So there are a number of log ratios that are available, and the original log ratios that were proposed by Aitchison are called the additive log ratio transformation and the centered log ratio transformation. So in the additive log ratio transformation, we take a log of the parts and with respect to one of the particular parts. So here the parts xt is taken as a reference. And so if you do it like this, then of course we can calculate the inverse ALR and go back to the original composition. So one of the things we notice, of course, is that this is asymmetric. And you would wonder whether or not this depends on xt, the choice of xt, and it turns out, and that's what Aitchison showed in his 1986 paper, that indeed this doesn't necessarily have to be dependent on that particular choice. It does, however, make somewhat the interpretations a little bit more complicated because we do have to make a choice with regard to xt, and so we would have to do our calculations with a particular choice. To circumvent this a little bit, we can also calculate what are called the centered log ratios. So here we center around the geometric mean. So the geometric mean is simply this equation here. So it makes sense to take a geometric mean and not a arithmetic mean when we're dealing again with logs and log ratios. And so again, then I get a back transformation. We notice one thing that's different is that here I have only d-1 components, and here I would have actually d components. As we mentioned before, our space, which is no longer a Euclidean space, but is called the Aitchison space on the simplex, has an inner product and inner distance. And so the previously defined inner product and the differently defined log ratios are invariant under permutations of the parts in the composition. And so that is an important property that that is true for both the ALR and the CLR log ratio analysis. So the philosophy then, as mentioned before, of the log ratio analysis is that we formulate the compositional problem first in terms of the components of the composition of the parts. We translate that into log ratios. We transform those composition into log ratio vectors. We do our analysis on our log ratio data with the usual standard multivariate methods such as principal component analysis or clustering, and then we transfer back into in terms of compositions. So the properties, as I mentioned before, of the ALR and the CLR is that ALR is asymmetric. It's not isometric, which means it does not preserve the distances. CLR is symmetric, but because we're dealing here, because we transform into a d-dimensional vector, it gives singular covariance matrices, and then also the subcompositions are not coherent. So these methods have been widely used. They've been proposed by Aitchison, and they are still widely used. They're successful, but of course they do not provide a nice general solution to the problem. So if you would like to really expand our set of tools, our multivariate tools or statistical tools to deal with log ratios in general, we would like to have spaces within which angles and distances can be related to angles and distances in the log ratio transformation, so and then that other space. And so this isomorphism is something that's really desired in terms of a log ratio. So this then led to the paper in 2003 in Mathematical Geology about isometric log ratio transformations. It's a really nice paper. It's perhaps for students a little bit mathematical, but I will just give you a little bit the gist of the paper, and then the computations, the equations for ILR don't look as nice as they do for ALR and CLR, but they're still very easy to compute, as you can do this in MATLAB or Excel. So what's the real deal here? So when we look at defining spaces, the first thing we'd like to look at is to define orthonormal vectors that constitute a basis in a d-1 dimensional subspace. So again, we're dealing, say, with if we have a composition of d components, that we'd like to construct orthonormal vectors in a d-1 dimensional space. And so a general formulation of that is given here. So here is the definition of these vectors, and you can verify, and it would be easy to do, for example, if you do this in 3D, that indeed we can define two vectors that are orthonormal, that are orthogonal, and that have a norm that's equal to 1. So these are just the spaces. So now the reasoning is that instead of having these orthonormal vectors, we'd like to have compositions. And so what we do is we just simply take this, these orthonormal vectors, and we calculate the closure of the exponent of that vector. So that will then give us a composition, and that composition would still will be orthonormal with respect to the inner product. So if you calculate the inner product of these various components, then you'll find that orthogonality is indeed preserved, and parallelism is preserved under that inner product. And so now we have basically a set of orthonormal compositions. So this is a standard, let's say, standard composition. Of course, in reality, we have data and we have different compositions. So what we then simply do is to take our composition and project them. That means create the inner product of that composition onto that orthonormal existing orthonormal basis. And so then we have essentially a new vector, and that vector is then called the isometric log ratio. So you can see that the log occurs in there simply by the fact that we're using the inner product as defined before. So once we have that, we can go back. That would be just projecting back. So this is simply the same thing as we do, say, in PCA. We can always construct back once we have the orthonormal basis And so that provides us now with the isometric log ratio. Properties of this log ratio is that indeed everything becomes orthogonal. So here's an example in the two-dimensional case where I have an ILR. So V's have basically a composition consisting of V1, V2, V3. So with the previous equations, I can calculate what they are the coordinates, the ILR coordinates, and that would be creating a new space in which I have everything aligned orthogonal, things that are orthogonal, and things that are parallel come out the same way, and that can be then described, of course, also in a ternary diagram. So in that space, for example, you would have that you can model circles, which then can be projected back into this original compositional space. So this is nice because now we have a method of log ratio transformation that has all the properties that we were looking before, which was subcompositional coherence, scale invariance, permutation invariance, but has also really nice orthogonal properties such that we can apply the standard statistical toolbox within that space of these ILR log ratios. Okay, so let's now arrive now to the exploratory data analysis with CODA. So just like any exploratory data analysis, we'd like to look at some basic descriptive statistics to make some visualization of our data. Our data is multivariate, there are many samples. It could be as many as, say, 50 to 100 parts in this composition. So how do we get some insight into that? Those are all questions that we should be looking at in doing an EDA. One of the really important tools in doing this is the Biplot, where we can start discovering patterns between, say, association of certain components between log ratios, potentially in grouping of samples within these plots, and how we would interpret these grouping of samples. It'll possibly also help us in determining what ternary diagrams we should be looking at, could help us in understanding what log ratios we should be looking at, etc. So then we'll be computing orthogonal coordinates as before. So that would, for example, orthonormal would be the ILR components, but we can also look at ALR, CLR components. We'll not talk too much about dendrograms and balance diagrams, but feel free to read up on that in the HSM book. So what about zeros? Zeros are a problem, absolutely, when you take a logarithm. So we have a problem there. So either there are a number of things we could do here. First of all, is say they're not important, so let's just forget about that part. It could be important, so the zeros are essential. They're really important, so that means that there's something happening in that population that divides things into that are zero and things that are not zero. And so that means we could possibly look at two different populations and treat those zeros separately in that sense. Or the parts are important, then you don't want to, the zeros are basically rounded, possibly due to just measurement limitations. And so in that case, there are other techniques such as imputation in statistics, imputation methods that would be replacing those zeros with either low values or with mean values, and there's several imputation techniques that can be tried out. So just like in a standard EDA, we'll be looking at some descriptive statistics. So of course now we have multivariate data, and so the question is, what do we look at? First of all, is to look at the sample center. This is basically the closure of the geometric mean. So you calculate the geometric mean and you close it, standardize it. The dispersion matrix or variation matrix is simply defined as by elements Tij, that is the variance of these log ratios. So that matrix, so each element consists of this variance of a log ratio, and of course this is symmetric matrix. Then from that we can calculate the total variances by making the sum of all those individual variances. Here's a simple example or an example. These are geochemical data from volcanic lava in Hawaii. So looking at various oxides, as we notice here, and they have all this composition. Of course, silica has a big part into it, aluminum, manganese, etc. So the first thing would be to do some descriptive statistics, which they calculate the center of our data. That's that's that geometric center, which then also we'll see turns out to be the center of that ternary diagram. And we can look at other statistics. And here we see the total variance variation in data. And so that if you have two data sets, then you can compare this variance of this data set with the variance of another data set that you may have. So in a variational array, we can look at it in various ways. Because it's symmetric, we can look at the variance of log ratios, and we also, in the lower triangle, we can typically plot basically the mean of the log ratio. So it's the variance is the mean. And so then you would get essentially here a plot. And so we can color this with high variances. For example, we notice there's high variance in the ratio, log ratio between iron oxide and silica here, and so on. And so, for example, we notice already that there are components in here that are varying, and their log ratios are varying. So those would be probably very interesting components to then say go and do some ternary diagram analysis or look at those subcompositions. So this is already an indication of something that's tremendously varying and maybe important. Doesn't mean that these others are not important. Of course, there could be information in small variation as well. So be mindful about that as well. So just like we do in statistical analysis, we'd like to center our data. It means have a mean equal to 0. And so what we can do is just take all the parts and average them. So here we would then center by perturbation, essentially with the geometric mean. So basically my center data would be my original data and then perturbed with the geometric mean. And so remember that the perturbation was that operation that we had defined in the previous slide set. So the centered sample will then gravitate around the barycenter of your data, and so that will be helpful, as you see in the next slide, in visualizing better ternary diagrams. And so it will not affect the variation matrix or the total variance. So here we see the effect of the standardization, the centering, sorry, in terms of the ternary diagram. So on the left is our original diagram. You notice all our samples are sort of sticking out over here, and suppose we'd like to really focus on that area and center around these samples, then this will be the result. What we notice, of course, that the composition change, but they are these compositional lines are the straight lines essentially change, but they're still straight lines, and so that's a property of doing this kind of geometric standardization. So now we can also look at doing standardization in terms of variance. So the typical classical statistical methods would look at is subtracting the mean and then divided by the standard deviation. So or variance. So here we do that. We make the product. This was our product as defined before. This is our total variance, and so we can calculate now a standardized sample. And so again, this is helpful in ternary diagrams. So here is the result of that standardization with variance. So again, now you get your samples are much more spread out over the entire ternary diagram. So we can then do the combination of both, and then we get basically centering and standardization. So now we have to look, looking at the original samples or composition by the standardized values. So next to the numerical summaries, just like in standard EDA, we'd like to look at graphical summaries of multivariate information. So the biplots are important there, and biplots are not necessarily limited to compositional data. This is basically a general way of looking at information in a matrix, contained in a matrix. And so this is an example of a matrix here. Basically, we are looking at 22 abstract paintings, and each of those paintings we have calculated the proportion of area covered by colors, such as black, white, blue, red, yellow, and other colors. And so we'd like to basically not just make numerical summaries, but provide some graphical display of all this information. The case here that we look at paintings is actually quite interesting and refers to the theory of color. Goethe, as you know, is the poet who also wrote not necessarily scientific work about theory of color. He was interested in studying how humans perceive color, what colors they associate, what colors are considered opposite, what if one color occurs, does another color tend to occur at the same time. And so what Goethe discovered, which was interesting, I believe, was that the humans look at colors in terms of blue, red, and yellow. This is somewhat different than what Newton discovered, is that essentially, and as was still used today, is that colors are association of colors are based on red RGB, which is red, green, and blue. And so that can again be displayed in a ternary diagram, which is actually done here. And so the association of colors. So on the left side, we see Goethe's wheel of colors, so where the certain hues are arranged opposite of each other. And so that was based on his understanding of how humans perceived color. So how are we going to look at information or display information that is contained in a matrix? This is quite general way of looking at this. This is not limited to decomposition. So imagine you have a matrix Z, which is your matrix containing that information, just as that 22 by 6 matrix essentially. And so the classical way is, of course, doing eigenvalue decomposition. But the question with eigenvalue decomposition, which eigenvalues are we going to plot? Are we going to focus on U, or are we going to focus on V? And what does that actually mean? So in the biplot, we're circumventing a little bit that question by plotting both of them. And so the way that works is that we'll be writing our matrix Z as a product of two matrices, G and H transpose. And that can always be done. Of course, it's not unique. So the way we'll get to this matrix G and H is by doing eigenvalue decomposition and writing that matrix basically as an orthogonal vectors times a diagonal matrix times another set of orthogonal vectors. And this is the column space and the row space, as we have seen in algebra. So one way of getting to this G and H is writing like this, is saying, well, I take my lambdas and I create this ratio here. And then I take one part of that ratio to the left side and one part of that ratio to the other side. And now all of a sudden I have two matrices that are also orthogonal. So whose columns and rows are orthogonal. So this is basically what you get over here. So this is now the G matrix and this is the H matrix. So now you can make various choices of alpha. And so if alpha is 1, then we are back to the original decomposition and calls them principal coordinates, and we call that the form biplot. So that favors looking at samples. You can also look at standard coordinates. That would be alpha is 0. So now we're focusing on this part here. And those would be the standard coordinates. So that's called the covariance biplot. And that favors looking at the variation in variables. So the approximation in that plot favors the variables here. The approximation in that plot you're trying to make is favoring the dispersion between samples. So what about biplots for compositional data? Well, it's very simple. Instead of just looking at the data itself, the raw data, like a 22 by 6 matrix, we first calculate the coordinates. And that would be here the CLR log ratios. We calculate log ratios. For example, the CLR log ratios, put that into a matrix, and then we do eigenvalue decomposition or singular value decomposition on that matrix. And so what we end up in the end is to have a certain amount of positive eigenvalues. Notice that these eigenvalues are eigenvalues of Z transpose or Z transpose Z, they're the same. And then we have eigenvectors belonging to this and eigenvectors belonging to that. So that's just a standard eigenvalue or singular value position. So then we write the best rank 2 approximation. So because we want to make a plot in 2 dimensions, so we're trying then now to do is using these eigenvalue decompositions to try to represent as much information as possible in a 2-dimensional graph. And so the way this is done in the least square sense, at least, is by looking at the first 2 eigenvalues. And so we can also look at, these are singular values. For the eigenvalues, we can look at how much variance does that 2-dimensional plot contain relative to the entire data set. And so the answer to that question is simply to look at the first 2 eigenvalues and standardize it by the total. So this sum of these first 2 with respect to the total is the amount of variability that's contained in that plot. So it's very important to calculate this number, because you could be looking at, say, 30% of variance, which is very low, or you could be looking at 98% of variance, which is very, very high. So that 98% would then essentially mean there's a lot of redundancy in the information that we have, and can reduce it to a much lower dimension. So here is the example of the painting example, and looking at the biplot of the scalar. So these are those kind of log ratios we're looking at. On the left-hand side, we see the form biplot, and on the right-hand side, we see the covariance biplot. So we notice there are a couple of immediately striking things. First of all, we notice that red, blue, and black, white seem to be in this plot to be on the opposite sides. And notice or remember that in the form biplot, we're looking more at the dispersion of samples. So we're trying to approximate dispersion of samples. While in the covariance biplot, we're looking more at approximating the dispersion of the variables. So this idea of having red and blue on the opposite side and orthogonal to white and black, we notice that those are very striking features. And so those are in telling us a bit about the dispersion of colors in these paintings, and how that dispersion of colors, or that variation of that colors, can be explained by means of some simpler variables than just, like, say, six variables, which would be the 5 colors plus outer. And that's really the idea of first of all, of a biplot, is to get an insight into what are sort of the minimum amount of information that will be needed to explain the variation in our data. And it seems, at least what this suggests already, is that something with a ratio of red-blue and a ratio of white-black is going to be important, and will allow us to explain the variation in the samples that we observe. We also notice that yellow is collinear with blue and red, which is interesting. Okay, so we can, of course, add that all up, or back that all up with numbers. So it's useful to plot again this matrix that's the variational matrix. In the variational matrix, you see, for example, that there's high variance in the blue-red ratio. That's this value of 1.07. Same with red, yellow ratio, etc. So we can look at that again more in numerical detail. So in the form biplot, as I mentioned, is that the distances here that we see between these samples are basically approximate differences between the samples, not between the variables, and that, of course, measured in terms of log ratio differences, not in terms of actual proportion differences. Okay, what other information can we look at? Well, let's look at the correlation matrix, some selected log ratio. So we notice, if you look at the log ratios of, say, for example, red-yellow and then red-blue, we notice that there's a very high correlation between that. So that means that if I would look at the data of red-yellow versus red-blue, I would find a correlation. Now, the other thing I would find, and if you look actually in the previous slide, if you look at the length difference between red and blue and red and yellow, that length of that line, and you can measure that in that biplot, you'll notice that that difference is about 2.5. So the ratio between the distance to red blue and red yellow is 2.5. What that means in terms of correlation is that if I would plot red-yellow ratio versus yellow-blue ratio, but to the power 2.5, I would expect that is nicely correlated, and that's what we see over here. Is that correlation is really nice in looking at that. So again, this suggests that biplots can be used to determining, for example, what ratios we would be looking at and what correlations in ratios that we will be looking at, and what sort of correlations are we expecting to see. Another view of the same information is to look at these diagrams and to decide biplots and to just try to discover parallelograms. So, for example, here we notice the parallelogram between red, white, blue, and black. And so a simple analysis will show that for those is that the log of those proportions are constant. And that's the definition of that, essentially, of a parallelogram in a biplot. And that, of course, that means also that if I take now ratios of black, red, and blue, white, that will show up as essentially that the samples will show up to be correlated along those different ratios. So again, it's a way of saying, okay, how can I represent all this information that I have of all this data matrix into a simple plot and focus really on those correlations and ratios that are important. Final example is here has to do with looking at individual samples. So in the plot, what we notice here is that, for example, 14, 6, and 13, even 7, they're collinear, they're lying on a line, and certainly with respect to this axis, they are orthogonal. So here the same is we have that is orthogonal with respect to that line. So what that means essentially is that data that lies on perpendicular straight line will have near constant ratios across those paintings. For example, if you look at those paintings here, 9, 21, and 15, if you look at these are the proportion of black, white, and other, and particularly, as I said, related to those that are orthogonal, then we notice that those ratios are constant for these paintings. So it'd be around 1 here, around 2 here, and again around 1.5 to 2 there. We can go even further, and with a proper sort of calibration of the plots, we can also look at actual compositions. So we can actually draw, for example, axes along which we can measure the composition of individual. We can look at the log ratio composition of individual samples. Because remember that the data matrix has originally compositions or log ratio of compositions, and so by doing the right projections, I can in this plot find back what are the original log ratios of each of the samples. So, and that is still approximate, but that's depending on the eigenvalue composition and on the variance explained. This can be quite a good approximation. Okay. So in summary, we've looked at 3 types of log ratio calculations, ALR, CLR, and ILR. So ALR, CLR were the original ones and are relatively easy to interpret, but had issues around not being isometric. So in that sense, we had to calculate a new type of ratio called log ratio called ILR that allowed us to create an isometric transformation between spaces, and that allows us to preserve distances and angles, and so the interpretations of things become much more easy in that sense, and particularly applying standard multivariate analysis. For EDA, we looked at biplots. Biplots are interesting means of analyzing information contained in data matrices, and particular to compositional data analysis, it allows you to look at variation between the composition of samples and between the variation between the parts of the composition that we observe in the sample. So there are 2 ways of looking at the same information, and it's really important that as a visual means of doing possibly further analysis and trying to see what kind of ratios you will be retaining for further analysis.